Hi everyone. It seems that we had some audio difficulties, and we tried to resolve the problem. We connected twice. I'm hoping that everyone can hear me now. My name is Isabel, and yes, I'm being notified via the chat window that you can hear me now. Thanks God. So you are going to hear a webinar about pinch analysis. The webinar will be presented by one of our experts at ProSim, Mr. Stéphane Deschalotte. All your microphones are off. Please, to ask your question, use the question dedicated window on the panel. We may not be able to answer all of you live today, so don't worry, we will take some time after the webinar to answer your questions, and there will be also a follow-up done with you. I will now let Stéphane speak.
Hello to all of you. I don't know if I have to say good morning or good night, since we have people from Japan, United States, China, New Zealand, and many other parts of the world. Anyway, welcome to all of you. Let us start because we are already late and we have many things to see today. First, what is at stake? A recent detailed study performed in France quantified the waste heat available in industry by temperature levels. This amount appears to be 51 terawatt-hour for waste heat over 100 degrees. That is for France. That represents 16% of the total fuels consumption in industry in France, but I am afraid that this figure is nearly the same in all the countries all over the world. And most of the heat of the energy used in industry is in process industries. So process people like us must do something to take advantage of this huge energy resource. 16% of the total fuel consumption in industry is waste heat over 100 degrees. What we will see today, first I will give you a brief overview of ProSim company. I will introduce pinch analysis, and then I will tell you what is behind advanced energy audits, and I finish by concluding remarks. I will not present in detail our software, nor do any software demo today. Regarding ProSim, our skills and competencies are in the field of process system engineering. We do mainly process modeling, simulation, and optimization. Among these fields, that includes thermodynamics, flow sheetings, etc. And one skill in particular is energy integration, process intensification, and pinch technology. Our clients are for all the process industries, ranging from chemical and petrochemical processing, oil and gas production, petroleum refining, energy, and many other fields such as air separation, biofuels, etc. And our clients are both operating companies as well as engineering companies, or also equipment manufacturers in these fields. And they use our software for conceptual design, optimization, and performance monitoring. Among all these process domains, we have some key domains. One of them is fine and specialty chemicals, gas, etc. In those domains, we have particularly relevant software, we have good references, and we have a long time experience. And among these domains, there is one which is energy efficiency. We are located initially in Toulouse, in France. We are calling you from France. And we also have, we established a subsidiary in Pennsylvania, in Philadelphia, several years ago. And we have a network of partners all over the world which are representing our software. Today, we have over 1,000 clients in 73 countries all over the world. The solutions we propose are both software, which is the most known of our activity. So we have a consistent suite of software. I will not detail this today. That's not my purpose. software that we will have a brief view today is our pinch software called Similis Pinch, and also some words about our process simulation software, ProSim Plus, which may be useful in complement of Similis Pinch. We also provide services, classical training, maintenance, and support of our software, but we also do process studies through modeling and simulation. In this, part of them are advanced energy audits. We also do application implementation and software extension in order to fit particular needs. And we also do some specific software application development and support, and also support and maintenance of legacy codes. But the purpose of our webinar today is mainly advanced energy audits. That's for ProSim. I will try to introduce you now basic principles of pinch analysis. Here is a flowsheet diagram of a process. Usually, such a process requires energy inputs, which are given from hot utilities or cold utilities, depending on if you want to heat or cold equipment in the process. And you can also have some other utilities, such as electric power, or other utilities, even such as compressed air or things like that. What is the usefulness of pinch technology? Pinch technology mainly aims to reduce the process energy inputs, which are supplied by hot utilities and or cold utilities. That's a basic idea, but it mainly proceeds by quantifying first the thermal energy that may be recovered within the process. That's what we call the energy targets. It also helps in supplying utilities at the appropriate temperature level. The acronym here stands for Grand Composite Curve. We will see in more details what is behind this. And last point, it also helps in finding how to value as much as possible this available thermal energy within the process. That is also called the heat exchanger network design. I will go to very basic things very rapidly. Here is an example with two process streams. I plotted on a graph the temperature of the stream. Here is the stream to be heated from 30 to 70 degrees. Here I represented another stream, which is a stream to be cooled from 50 to 20 degrees. I know what I do. The idea, which is trivial, is to heat the cold stream with a hot stream. We see the heat exchanger that is done for years in the industry. So we plot on the same graph both segments, one for the stream to be cooled and one for the stream to be heated. And when we place those two segments on the same graph, one way to do is to call the hot stream by providing cold utility and to heat the cold stream by providing hot utility. Here, when the difference temperature between both segments is 20 degrees, we have no heat recovery at all. But when we reduce this temperature difference, delta T, between both segments, both curves, we can start to have heat recovery between those two streams. And if we reduce further the delta T, the heat recovery increase. So we can see that's a general thing that when the temperature difference between those two streams decrease, the heat recovery increase. So the utility requirements usually decrease, that's the operating cost. But as you have to increase the heat exchange area, the investment costs, the capex, are increasing. So that's for a simple case of one heat exchanger. We'll see further that there is a trade-off between capex and opex in order to find the appropriate value of the temperature difference between those two curves. The pinch analysis has been developed in the early 80s and has been popularized also by Professor Bodolinov at University of Manchester. He published a lot and worked a lot on this subject. The principle is, well, it's based on first and second law of thermodynamics, and the idea is to substitute as much as possible the energy requirements of each unit operation by an appropriate source of energy which is available at some other point in the process. What are the advantages of this method? First, it's a graphical method, so it's very visual and very didactic, so that's good because you understand what you do. But for me, the main advantage is that it's a systematic approach which globally optimizes recovery within the whole process as opposed to local optimizations. We all know that a local optimum is not the global optimum of process. So here, for instance, you have a very nice local optimization of heat recoveries at a boiler level. The flue gas, there is a number of heat exchangers in the flue gas line. So that's a very good optimization at this level. But if this boiler is within a whole process, if it's here, for instance, it is not sure that the design of heat exchangers here is the most appropriate one, because this flue gas available at over maybe 800 degrees may find better utility in other parts of the process. One strength of the pinch analysis is this one, is the optimization of heat recoveries within the entire process. That's an important point. I will now detail step by step rapidly what is behind pinch analysis, how to implement it. First step is the process flows to be heated, so such say cold streams, and the process flows to be cooled, the hot streams, are listed for the entire process to be analyzed. And for each flow or stream, it's a process mass flow between two equipments, you have to know the initial temperature, its final temperature, its mass flow rate, and it's also its specific heat. In fact, you need the product mass flow rate multiplied by Cp, by specific heat, expressed in, for instance, in watt per kilogram or per Kelvin, sorry, or in kilocalorie per Kelvin and second. Because the duty is computed by FCP delta T. So this step of listing all the streams which needs to be cooled and the streams who needs to be heated, which is fundamental, is not as simple as it seems to be. First, in many cases, a tentative heat integration has already been done, and it must be ignored to have a good pinch analysis of a process. So that's for an existing process here. You can see on one side 3 hot streams from 250 degrees. They are represented here from 250 to 200, and then from 200 to 50, and also 3 cold streams. That's a way to do it, but that's not the appropriate one, because in fact you have to ignore this heat integration which has already been done, and the proper way to do it is to consider only 2 streams, one cold stream, which is the process feed, which is available at 50 degrees and which is needed at 200 degrees at the entrance of the reactors here. That's a cold stream here. And you have one hot stream, which is the output of the reactors, which must be introduced in the separation column at 50 degrees. So you have to consider here only 2 streams. So always ignore the tentative heat integration which has already been done. That's the first issue. A second issue, how to proceed when 2 streams at different temperature are mixed. There is no heat exchanger here, but both streams are mixed at the outside of these heat exchangers. So here you have to consider that you have one stream which is going from 20 degrees to 112, and another one which is going also to 20 degrees to 112. You have 2 cold streams to be heated here. How to manage utilities? Here, for instance, you have a stream going from 20 degrees to 223 by means of steam, available at 236 degrees. Do you need to consider this steam as a cold stream or not? Usually we don't. The steam must not be taken into account in the list of hot streams. So you have to ignore also the utilities which are supplied to the process in the current design. Another difficulty here is that many streams may be existing in the process. So this step of listing all the streams may be tedious. And in many cases, the stream data is not available straightforward. You have to look for them. So this step of called also data extraction is fundamental to get good results from a pinch analysis. Second step, heating requirements of cold streams and cooling requirements of hot streams are combined into composite curves. That's a magic word. You will also find in the literature temperature enthalpy diagrams or other wordings, but it's always the same thing. I will show you how these composite curves are built. Here I represented two hot streams on the same diagram, one with heat duty F1 CP1, the other one F2 CP2. These two curves representing two streams are combined in one single curve called the composite curve, and in the range where the temperatures overlap from here to here. These two segments are combined in one segment having a heat load of F2 CP2 plus F1 CP1. So like this, you can combine all the streams of the available on your process, all the hot streams on one side and all the cold streams on the other side. You get here, in this case, 3 segments with different FCP. Then both composite curves are placed on the same diagram, and for hot streams, the red one, and for cold streams, the blue one here. And the cold composite curve is moved horizontally. All points of this curve must be at least at a vertical distance of delta T mean of the hot stream curve. So you get this kind of diagram where you can see the hot utility requirements. Here you can see the bottleneck where in the heat exchange recovery system, which is a pinch point of the process. And when there is overlap of the curves, you can have process heat. There is potential heat recovery within the process between those three and between hot streams and cold streams. And also you can visually see the hot utility requirement and the cold utility requirement of this process. So some definitions of words. The minimum temperature difference between both curves is called the process pinch. The central part of the graph, here in green, where both curves overlap, is the heat recovery, where there is heat which may be recovered. The left part of the graph, where there is no overlap, represents hot streams requiring to make use of cold utilities. Here, the bottom of the graph, you have the cold utility requirements. And the right part of the graph, where there is no overlap, represents heat that must be supplied by hot utilities, the hot utility requirements. And for each value of the process pinch here, you have one maximum heat recovery called MHR, a minimum cold utilities requirement, and a minimum hot utility requirements. So first you have to decide when you will make a pinch analysis which pinch you will use. Those maximum heat recoveries, those minimum cold utility requirements and minimum hot utility requirements are also known as the targets. So you have to find the pinch value which will give the minimum global cost for all the process. So usually when, as we have already seen on one heat exchanger, when the pinch decrease, the heat recovery increase. So the utility requirements will decrease. That is this red curve here, red line. So the OPEX are decreasing, but at the same time, the investment, the CAPEX, investment costs are increasing because you have to add a heat exchange area. So it's a matter of trade-off between those two. So if you plot the sum of those two curves, usually there is a minimum, which is optimal cost. So one way to do is to plot this curve and to find the pinch, the optimal pinch that will give the minimum optimal cost. However, in the real life, it is difficult to plot these curves easily. In particular, the CAPEX cost, the CAPEX curve, sorry. It's difficult to get a reliable one because when you have different technology of heat exchangers, you don't have the same calculation of cost, so it's difficult to have a unique curve. So in fact, this analysis can be used only to get a first global view, assessing that only one technology of heat exchangers is used on the process of insulin tubes. However, in many cases, it is when you can take advantage of several technologies that the return on investment becomes interesting. Another way to do is to set the pinch value depending on the industry domains where you are. Usually in cryogenics is between 3 to 5 degrees, in petrochemicals is between 10 to 20, in refining is 20 to 40, and in chemicals in general is about 10 to 20. So when you have set the process pinch, you have your targets, the maximum heat recovery, the minimum cold utilities requirement, and the minimum hot utilities requirement. So that's already important because you know how far you are from what you can imagine to gain. Another possibility with the pinch analysis is to supply also utilities at the appropriate temperature level using the so-called grand composite curve. How is it plotted? When you have your composite curves here, you move down by half delta T mean the hot streams composite curve, and you move up by half pinch the cold streams composite curves. So both curves becomes like this. And then when you have those two curves, which are here at zero pinch here, you plot the difference between the cold temperature and the hot temperature as a function of temperature. So this distance is reported here. Here there is 0, so that's 0. Here you have this length here is reported here. So like this, you plot all your so-called grand composite curves. Here you can see directly the total hot utility, it's the same value as here, and also the total cold utility. So you assess the minimum and maximum temperatures of utilities. So you can provide all the utilities at this level, all the hot utilities at this level, and all the cold utilities required at this level. But also, these grand composite curves allow also to assess the quality, the level of temperature, which may have a cost impact. Sorry. You have the possibility to appropriately select the level of utilities. Here, for instance, instead of providing all the utilities at this high level of temperature, you can have both a high pressure stream and low pressure steam. In this case, this may have cost impact because low pressure steam is usually cheaper to produce than that high pressure steam. Sorry. And same for cold utilities. So with this grand composite curve, you can decide the appropriate level. That's one way That's one use of this grand composite curve. This grand composite curves also allows to detect the opportunity to place on your process some thermal machines, such as heat pumps, thermal engines, organic ranking cycles, and things like that. Here, for instance, you have this kind of grand composite curve, and if you want to place a heat pump, it will be easy because with a very low temperature difference provided by power here, you will increase, you will have a great utility savings because this segment is very long. The next step is to find a heat exchanger network which will be able to actually recover the maximum heat recovery. That is also called the synthesis of heat exchanger network. At this level, there are several approaches available. The first one is a graphical approach. It has been detailed by Bodolinov. The pinch point divides the problem into two parts, which are designed separately. And Linov gives some rules in order to build a good heat exchanger network. And so this design is performed, let's say, manually. It's usually tedious. It's a complex task. Another approach is a, let's say, mathematical approach. It's usually MENLP optimization. It usually gives the best results, but it requires high computing time when there is more than 3 or 4 hot streams and 3 or 4 cold streams. It's not appropriate in general for most industrial actual processes. And also one limitation of this approach is unable to mix heat exchanger technology. The capex of heat exchanger is obtained by a single equation. So that meaning that you have all the heat exchanger technology which is the same. You cannot mix a plate and frame and shell and tube heat exchanger, for instance, on your process. So the last approach is the approach we decided to implement in our software with our proprietary algorithm, which gives, let's say, good networks, which is not always the optimal one, but it's an efficient one. One of the main advantages is that it is very fast, thus allowing to test many configurations easily. And it's well suited for revamping. Site operation constraints can be easily taken into account. So it's available, Simulus Pinch is an energy integration of processes which is available directly as a Microsoft Excel add-in. So all the features required for an advanced energy audit are available in one tool. You can plot the composite curves, set and calculate the energy targets, etc. directly in this tool. It's a standalone solution which can also be used in conjunction with a process simulation software. I will explain here how. Process simulation can be a useful complement in order to obtain missing data, the step 1 data collection or data extraction, and also take advantage of an automatic data pre-processing. Before using Simulus Pinch, you will get all the list of streams and their initial temperature, final temperature, and product FCP. So the data extraction, the step 1, can be done fully automatically within ProSim Plus. It will select all appropriate streams, which is not always easy, as I mentioned before, and it will export the data automatically to Microsoft Excel. So here it's, by one click, you will get all the information available in Excel, and the advantage that you can further process your data in Excel as you want. And you can also use complementary software such as Simulus Thermodynamics, etc. Also, it is useful to guarantee the global consistency of the data from a mass and energy balance point of view. If you use process simulation software, you will have fully consistent data. Also, using process simulation, will allow you to be able to generate equipment specification sheets, data sheets, which will be useful for you when you will deal with heat exchangers manufacturers. You will be able to virtually test the process changes, which will be suggested by the pinch analysis. And you will also be able to improve the pinch analysis results with an exergy analysis. In ProSim Plus, we also provide exergy balances in addition to mass and energy balances. And this will also give you further improvements of your energy consumption. One key point is the automatic and fast design of an efficient heat exchanger network. I will give you here a simple example. Is taken from Yi and a publication from Terence Yi and Ignacio Grossman from Carnegie Mellon University. In the paper they published, they obtained these heat exchangers by a MINLP algorithm, so a heavy mathematical approach. They found 5 process heat exchangers. They have 3 hot streams and 4 cold streams in this example. And they found 5 process heat exchangers, 3 utilities heat exchangers, hot utilities required of 540 kilowatts, cold utility requirements, and a capex of about $151,000 US. Using Sibyllin pinch, here is another way to represent the heat exchanger network. We obtain 4 process heat exchangers, 5 utilities heat exchangers. The hot utilities required are of 362, is 178 kilowatts less than those calculated by Grossman. The cold utilities required is higher in our case. We have 18 kilowatts more. And our capex are very similar, is only 1.4% more than the heavy mathematical approach. So as I said before, simulation pinch will give you a good heat exchanger network, but not always the optimal one. However, you will get the results in less than a few seconds, so it's very fast. So you have a great configuration flexibility to allow use in design as well as in revamping, because most of you are in operating companies where they mainly have to do revampings instead of new process design. So it's important to use this tool also for process revampings, and it's in Microsoft Excel, so in order to make use of allowing simple results analysis. But the key point from pinch software is the heat exchanger network design. You will find over the internet many free software for plotting composite curves. There are a number of them available for free, but good software for heat exchanger network design, they are much less. So that's an overview of the pinch analysis and introduction. Now I will give you some information about what is behind advanced energy audits. Well, within the European Union, energy audits are mandatory for most companies, so we are obliged to do them. In France, for instance, companies over 250 employees, over 50 million turnover, and a total equity over 43 billion euros must comply with this obligation. The audit must cover 80% of the energy bill. The scope of the audit is buildings, processes, transport, etc. All the source of energy consumption. These audits must be renewed each 4 years, and the auditors must be certified. Companies which are ISO 50001 are exempt. The cost of these mandatory audits are a few kilo-euros per industrial site. So for this price, they are not very detailed. They are also called walk-through audits. And most companies perform these audits only to comply with laws and regulations. We are not in this market, clearly. We propose what we call detailed energy audits. Here I will give you some detail on our methodology for the detailed energy audits. First step is assessment of energy targets, then energy process integration, and finally process proposition of improvements of the process. So if I detail each step of this energy audit in our methodology, we have first contacts. We start with first contacts with the operating companies. We get preliminary description of the plant. We assess and agree with the plant owner on the audit objective and scope. We issue a code, cost and schedules. And if it is accepted, the plant owner gives us a purchase order. We have an audit kickoff meeting in order to secure the understanding and the objectives and constraints, in order to improve of process knowledge also, and to determine the key performance indicators. And we establish a preliminary list of data which will need to be gathered. Second part is the data gathering. This step is fundamental, as I already mentioned, to get reliable and useful audit results. Then one or several audit visits in order to gather data which is required for analysis and missing data. Analysis and consolidation of the data which is gathered, discussion with operating staff also to verify the data collected, and when some process data remain unavailable at this level, we can simulate all or part of this process to virtually get this data. Then we will have the calculation of the energy targets based on pinch technology. So assessment of an appropriate pinch value, determination of the maximum heat recovery, and the minimum hot utilities requirements and cold utility requirements. And we will compare these values with the actual process consumptions. So at this level, Simulus pinch is used, and sometimes ProSim Plus to perform this part of the audit. And then there is a report drafting and presentation of these first results. Then there is the energy process integration part, which is the most complex one. Process energy integration. So here is the automatic design of a heat exchanger network, which will recover almost the maximum heat which can be recovered. The proprietary algorithms that we use select among all the possible heat exchangers complying with user criteria, those which are appropriate with regard to selected criteria. And specific constraints can be taken into account. That's an important point. Here is a screen of Simulus pinch, just to show you the kind of constraints which can be taken into account. Some constraints may be also, you can restrict the exchange to a zone, an area of the process. You can give an incompatibility matrix. You can forbid to have exchange between several streams, because maybe there is a risk concern. Also, you can give a maximum difficulty matrix. So the difficulty of each exchange can be given for each stream. And also you can have some mapping constraints. You can give, for instance, a maximum distance for exchanging the heat between two streams in your plant, depending on your own layout. So for this pinch, Simulus pinch, for this step, Simulus pinch is used. That is clearly the most tricky part of the energy audit, and that is where Simulus pinch demonstrates to be very powerful, because you can test very fast several configurations. And last part is a proposition of improvements. Opportunities may be detected during the first steps of the audit. When you visit the plant, a detailed inspection of the process unit operation after unit operation during this data collection allows to point out some areas or equipment items where corrective actions are required. For instance, you will discover a non-expected heat exchanger fouling, distillation column flooding, or some steam venting which is not known by the operating staff. At this level, also remind that some light process improvements may lead to huge energy efficiency improvements. Example of the adjustment of a distillation column reflux may change totally the heat consumption of the plant. There are improvements which are suggested by the pinch analysis itself, as we have seen before. You will add new heat exchangers. The duty of each new heat exchanger will reduce hot and cold utilities requirements. You can decide to add thermal machines, such as heat pumps, organic ranking cycles. You can provide the utilities at the appropriate temperature level using the grand composite curves, as we have seen before. And you also may detect some cogeneration opportunities. Finally, you also can have improvements which are suggested by an exergy analysis. By the exergy analysis, the irreversibility within some unit operation may be detected, and loss of exergy in effluents and production streams may also be quantified. So at this level also, some opportunities may be pointed out, such as methanization of some effluents, combustion of some waste streams which have a high low LHV. There are also some opportunities at the utilities production level, boilers efficiency improvements. You can add heat exchangers on the flue gas line. You can improve the boiler feed water deaeration. You can recover heat on condensates, etc. And you can also place turbine and waste steam. So there are also opportunities at the utilities production level. So some concluding remarks for these energy audits. We have a long experience in this field and we have completed many projects. We have expertise in this field. We have a team of engineers which are trained and experienced in performing such energy audits in industry. During this advanced audit, our process background allows us to go much further than simple mandatory and legal audits. Those audits are not limited to chemical processes. We have experience in food industry, in pulp and paper. These kind of processes can also be tackled. Where is the difficulty is with batch processes, because the methods are not as well suited. You have to store energy, so it's a big concern. And what are the results that may be expected from such an audit? Usually, it's a reduction of about 20% of the energy bill. But on some units, I remember an example in a biofuels plant, for instance, we reduced the energy bill by 40%. And the return on investment, including the studies and the capital costs, are usually much lower than 1 year. So to conclude, the technologies are mature today. The tools are available. The gain that you may obtain may be substantial. Such methods require some expertise, and using appropriate software may be very useful. If you want to go further, from our website, you will see that we organize trainings. You will find more information on Similis Pinch with some getting started to learn more about the software. Same for ProSim Plus. And regarding the literature, there are many sources available. Here there is, I mentioned one book, but there are many sources available to get get into more details into this pinch analysis and energy audits. That's it. Thank you for your attention. Maybe there are some questions we can try to answer. No, no questions. That's perfect.
Thank you for participating to one of ProSim webinar. We hope that this webinar met your expectations. And ProSim's teams remains at your disposal to collaborate on your simulation and optimization projects. Please don't hesitate to contact us via our website or just call us. And you will also, just before leaving the webinar, you will be asked a few questions. Please kindly answer them so we can improve our webinar. And obviously, you will also receive the replay of the webinar later this week. So bye, everybody, and enjoy the rest of your day. Bye.
Thank you. Bye-bye.